The views expressed in this interview are those of the individuals and do not reflect the official policy or position of the U.S. government, the Department of Defense, the U.S. Navy, or the Naval Postgraduate School. Welcome to the Trident Room, brewer of stout conversation, unfiltered and on tap. On today's episode, Trident Room host Karl Flynn sits down with Dr. John Arquilla and Dr. Peter Denning.
Going all the way back to the beginning of the conversation, talking about the difference between artificial intelligence versus automation, there are a few distinctions that you make in the article talking about different ways to achieve different effects in terms of what we, in popular perception, might be considered AI. And so one of these new promising technologies is the neural network. And so I'm just looking directly at the article here. And it says that a neural network is organized as a series of layers that process stimuli through successful levels of abstraction until they become responses. Because they have dozens of levels, they are called deep learning networks. And in the following paragraph, it describes how a neural network is not programmed in the sense that you would code a normal computer program, but rather they are trained by an algorithm. So what about these neural networks allows them to closer emulate what we would consider intelligent behavior? And then one problem that you also outlined is inscrutability. So could you explain also what inscrutability is and what the ramifications of that problem might be?
So first of all, let's go back to the issue of the early expert systems, which were supposed to simulate expertise, supposed to be like experts. Mm-hmm. So, and it was all believed that experts behave according to rules. So if we knew all the rules that an expert uses, we could program them into the machine. And if we know all the facts that the expert relies upon, we could put them in the database. And the ones that succeeded tended to be the ones that did diagnostics, like medical diagnostics and mechanical airplane diagnostics, where the rules are much clearer. Okay. So the expert system project was never able to achieve expertise. It was never able to, like simulate an expert doctor, and do that. And since nobody was ever sure of whether an expert system was giving you the so-called correct result, they also insisted that you could ask the expert system to outline the logic that it used to reach a conclusion. And the expert system knew what rules had been applied and could say, well, this didn't work the way most people wanted. Expert systems were never able to become experts. There were many debates around why this was so, but the fact remains that they didn't do it. Well, in the modern age now, all that argument took place in the 1980s. And now we're 30, 40 years later than that, we have new technologies. And one of the new technologies is the neural network. The neural network is organized on a different principle from rules. So the early expert system was associating input and output by applying rules to it. And the neural network is being asked to do that sort of like directly. So we know rules got used to get from input to output, but we can associate them together. And the neural network would remember that association. And if we showed the input again, it would immediately tell you what the output was. And one of the most obvious uses of this was in face recognition. So we could represent an input by a bitmap. Your camera puts out these, nowadays they put out 12 megabits or whatever they are, megapixels. So that's the picture. And you present that to the neural network along with what let's say there's a face in this picture, and then let's say it's my face, Peter Denning. So you present these two things to the network, the image and the name, and you tell the network to remember this image. So if I ever show you the image again, you output Peter Denning. Okay, and then how do we make the network remember that? Well, this depends on the structure of the network. The network is built of a series of layers of simulated neurons, which have inputs from other neurons with weights on them, and a rule that says if the total input to a neuron exceeds, with all the weights applied to it, exceeds a threshold, it fires. And then that output gets distributed to the next layer of neurons. So the algorithm does is it goes through this and adjusts the weights all throughout that network so that when I show the picture of Peter Denning and the desired output that's the text of Peter Denning, the network gets adjusted so that whenever I show that picture, the output is immediately achieved. Just all the flows of information go through that network and out comes Peter Denning. Okay, so this is a different organization of how you process the data. And the result of it was we were able to recognize faces. We didn't know how to do that before. And it's now it's ubiquitous. It's on your phone, it's in Facebook, airports use it, everybody. One of the problems that's been found with this is starting to turn up, when police were using face recognition to see if they could detect persons who had previously committed crimes, so that they can pull them over or at least associate them with the crimes. And these systems tend to make serious errors. So you show them a picture of somebody and I would say that's not John Smough, it's Joe Smith. Okay, and it really was John Doe, but the machine said it was John Smith, and so the police arrested this other poor guy, and he has to go through torture and torment to get. He said, "I've been accused by the machine, and this is unjust." So this has brought the problem to light. That it now gets called bias. They say somehow there's bias in the training data, so that when you operate the machine outside the lab where it was trained, and you're like in the real environment, the pictures you're showing it are not the same as the pictures it got trained on, and it makes mistakes. And sometimes these mistakes can be very costly.
Well, Peter, hasn't this happened with self-driving cars as well?
Yeah. So this has been called the fragility problem. Is even a well-trained neural network, which can do some pretty amazing things, can make mistakes. And if it's in being used in an environment where a mistake has a high cost to it, it becomes dangerous. And John, you had an example in Afghanistan, I guess, during the evacuation with one of these systems. Could you say something about that?
Sure. To detect whether a terrorist is going to come in with a suicide bomb or some kind of act of sabotage, and the neural nets supposedly learned that this attack was underway because it fit all the parameters under which it was operating, and it ended up being a family simply trying to get to the airport, and they ended up being killed. And a human being made that choice, not the machine, but the machine gave the information upon which the human choice was made. So this whole idea about not letting the machines make these kill decisions, as they call them, misses the point that humans will rely, if they believe in these systems, they will rely on them to their detriment. And as I mentioned a moment ago, we've seen a couple of examples of this fragility problem in self-driving cars that have led to some terrible accidents already. So I think we need to be very cautious the venues in which we rely on these, because often we can rely to our detriment. As a single incident of killing an innocent family using this system now clouds its use in a very broad way in security settings. That said, there are other settings where there is a learning process, and we like the term machine learning a lot, where, for example, AlphaGo, which plays this Asian strategy game, It's got 361 points upon which black or white stones can be put almost anywhere on any move. And AlphaGo was simply given the board, the rules, and then it played 390 million games against itself to see what worked, what didn't. And then it went up against the world champion Go, or now they're not self-aware, they're not intelligent in the sense that people like to use the term intelligence, but these are automated systems that can learn, and again, in very specified rule set areas, can do some quite remarkable things. And this isn't just in chess or Go or board games. This can also be used in larger strategic settings. I remember before I came to the Naval Postgraduate School over 30 years ago, and was still at the RAND Corporation, we had a RAND strategy assessment system that exhibited some of these learning of the programming of these in terms of scenarios. And if you were careful about what you inputted, very basic, sort of, here's the general context. In that case, it was the matter of Persian Gulf security. The assessment system was a very nice adjunct to human judgment. And I think that's probably the baby step we want to take in terms of using artificial neural networks and machine systems of a ship or an AI in a fighter plane, but actually in making higher order decisions about providing security for an evacuation in Afghanistan or operations in the Taiwan Strait, et cetera. So I'm reminded, Peter, of something Claude Shannon wrote 70 years ago. He said, "One day we will build machines that are exceptionally powerful. They will see far, but notice little. They will remember everything, but know nothing." It seems to me that he both addressed issues of context and fragility with that statement. And it remains something that I hold very close and keep in mind whenever thinking about these issues.
Yeah. If I might just add something to that, some of it has a different structure from standard programs and is therefore able to do some certain things like face recognition or handwriting recognition better than, in some cases, way better than a human being. If you had, for example, a customs officer sitting at a booth, they don't have the mental database of everybody that's coming through, so they refer to a computer database. Okay, so there's definitely an advantage that you can do things if you have a huge database. But the question is, can you overcome this fragility issue? Some people said, well, because the neural network in some very, very loose ways is structured like a brain in the sense that it's built up of parts that look like a neuron with inputs and outputs, and plug those all together into a dense network that somehow looks a little bit like the brain, or at least as far as we know what the brain looks like. That we built a structure that more resembles the brain than the expert system structure with rules. And therefore, maybe this system will be able to do things better that the rules can't do. Well, that's true. So the structure allows it to do some tasks that the rule-based system can't do. But on the other hand, it remains fragile. It remains that if you put it into a different context from which it was trained, it can make mistakes. And nobody's figured out how to overcome that. So in a lot of cases, these things like, if it's a kill system and it chooses to annihilate a vehicle, and the vehicle contains an innocent family, then it does matter that the machine made a mistake. So we just can't brush it aside that the machine made mistakes. And a lot of people are looking into the issue of, can we strengthen these machines so they don't make as many mistakes? And but there's a lot of people looking at it.
Very, very valid points. the two problems that you're discussing, inscrutability and fragility, going back to the article, there's 2 points talking about inscrutability. There's one very interesting quote here. You write, "The question of explaining how a network reached its conclusion thus cannot be answered by an examination of its connection matrix. It would be like trying to examine the dark motives of criminals by examining their brain scans." That's, when you frame it that way, where does one even begin to solve that problem is the first thought that comes to my mind, because that, again, like you said, it's not rule-based, it's based on the network. And then talking about context being put in a data set outside of what it recognizes. I believe, Dr. Arquilla, you brought up the self-driving car example, and one of the references you have, it says that a self-driving car was confused when it saw speed limit signs with bird droppings on them. So that's another question of, in my mind, again, to us humans, obviously you can tell that's still a speed limit sign, but then how do you get the machine to recognize that? So very valid points, and very interesting to see how that proceeds in the future. Gentlemen, this has been a tremendously interesting discussion.
I would just add that for all our concerns about this over enthusiasm about the potential of artificial intelligence actually to be intelligent, we see tremendous opportunity in terms of exploiting and advancing the applications of automation. And in my own view, automation in the 21st century will have as profound an effect on military and naval warfare. For our own adversaries in the world are already doing this. And it's almost as though the new arms racing is not so much to build weapons as to try to build new forms of understanding and information systems that will greatly enhance the effectiveness of military and security forces. So I hope that the skepticism about, quote, intelligence that we've expressed in no way dampens the enthusiasm to pursue automation to its fullest potential.
Dr. Denning, any last thoughts from you, sir?
All I ask is let's feet on the ground and make sure that all the claims we're making are well-grounded claims, backed up by good science and good engineering if they're applying to the way a system works, but also backed up by good philosophy and strategy and understanding how geopolitics and how people in different nations see things and work. So all these things go together, and they can't really be pulled apart. Not just the world as seen immediately by the operator of the system, it's the whole geopolitical context in which the conflict is taking place. And somehow or other that has to be part of the way we learn how to think. So I'm hoping we can get away from the hype and be serious about understanding all these issues as we move forward.
Hard to argue with that, gentlemen. Well, with that, thank you so much for your time.
Thanks for joining us in the Trident Room. For more information about today's guests and topics, please visit the show notes. The Trident Room has been brought to you by the Naval Postgraduate School Alumni Association and Foundation. For questions, comments, and suggestions, please email us at tridentroompodcasthost@nps.edu and find us online at nps.edu/Trident Room Podcast.